Section 11.3, Authentication with OpenID Connect, JWT, and Keycloak. At the moment, users must log in via a browser with a username and password. Since Keycloak now manages user accounts, we could go ahead and update Edge service to check the user credentials with Keycloak itself, rather than using its internal storage. But what happens if we introduce different clients to the Polar Bookshop system, such as mobile applications and IoT devices? How should the users authenticate then? What if the bookshop employees are already registered in the company's Active Directory, AD, and want to log in via SAML? Can we provide a single sign-on, SSO, experience across different applications? Will the users be able to log in via their GitHub or Twitter accounts, social login? We could think of supporting all those authentication strategies in Edge service as we get new requirements. However, that is not a scalable approach. A better solution is delegating a dedicated identity provider to authenticate users following any supported strategy. Edge service would then use that service to verify the identity of a user without being concerned about performing the actual authentication step. The dedicated service could let users authenticate in various ways, such as using the credentials registered in the system, through social login, or via SAML to rely on the identity defined in the company's AD. Using a dedicated service to authenticate users leads to two aspects we need to address for the system to work. First, we need to establish a protocol for Edge service to delegate user authentication to the identity provider, and for the latter to provide information about the authentication result. Second, we need to define a data format that the identity provider can use to securely inform Edge service about the identity of users after they have been successfully authenticated. This section will address both issues using OpenID Connect and JSON Web Token. Section 11.3.1, Authenticating Users with OpenID Connect. OpenID Connect, OIDC, is a protocol that enables an application, called the client, to verify the identity of a user based on the authentication performed by a trusted party, called an authorization server, and retrieve the user profile information. The authorization server informs the client application about the result of the authentication step via an ID token. OIDC is an identity layer on top of OAuth 2, an authorization framework that solves the problem of delegating access using tokens for authorization but doesn't deal with authentication. As you know, authorization can only happen after authentication. That's why I decided to cover OIDC first. OAuth 2 will be further explored in the next chapter. This is not the typical way of covering those subjects, but I think it makes sense when designing an access control system like we're doing for Polar Bookshop. Note: this book will only cover some essential aspects of OAuth 2 and OIDC. If you're interested in learning more about them, Manning has a couple of books in its catalog on the subject: OAuth 2 in Action by Justin Richer and Antonio Sanso, Manning 2017, and OpenID Connect in Action by Prabhath Siriwardena, Manning 2022. When it comes to handling user authentication, we can identify three main actors in the OAuth 2 framework that are used by the OIDC protocol. Authorization server, the entity responsible for authenticating users and issuing tokens. In Polar Bookshop, this will be Keycloak. User, also called the resource owner. This is the human logging in with the authorization server to get authenticated access to the client application. In Polar Bookshop, it's either a customer or an employee. Client, the application requiring the user to be authenticated. This can be a mobile application, a browser-based application, a server-side application, or even a smart TV application. In Polar Bookshop, it's Edge service. Figure 11.2 shows how the three actors are mapped to the Polar Bookshop architecture.
Figure 11.2. How the OIDC/OAuth 2 roles are assigned to the entities in the Polar Bookshop architecture for user authentication.
Note: the roles defined by the OAuth 2 framework are also known by different names when used in the context of OpenID Connect. The OAuth 2 authorization server is also called the OIDC provider. The OAuth 2 client, which relies on the authorization server for authentication and token issuing, is also called the relying party, RP. The OAuth 2 user is also called the end user. We'll stick to the OAuth 2 naming for consistency, but it's helpful to know the alternative terminology used in OIDC. In Polar Bookshop, Edge service will initiate the user login flow, but then it will delegate the actual authentication step to Keycloak via the OIDC protocol, supported out of the box by Spring Security. Keycloak provides several authentication strategies, including traditional login forms, social logins via providers like GitHub or Twitter, and SAML. It also supports two-factor authentication, 2FA. In the following sections, we'll use the login form strategy as an example. Since users will interact directly with Keycloak to log in, their credentials will never be exposed to any component of the system except Keycloak, which is one of the benefits of adopting such a solution. When an unauthenticated user calls a secure endpoint exposed by Edge service, the following happens. -1. Edge service, the client, redirects the browser to Keycloak, the authorization server, for authentication. 2. Keycloak authenticates the user, for example by asking for a username and password via a login form, and then redirects the browser back to Edge service, together with an authorization code. 3. Edge service calls Keycloak to exchange the authorization code with an ID token containing information about the authenticated user. 4. Edge service initializes an authenticated user session with the browser based on a session cookie. Internally, Edge service maintains a mapping between the session identifier and ID token, the user identity. Note: the authentication flow supported by OIDC is based on the OAuth2 authorization code flow. The second step might seem redundant, but the authorization code is essential for ensuring that only the legitimate client can exchange it with tokens. Figure 11.3 describes the essential parts of the authentication flow supported by the OIDC protocol. Even if Spring Security supports that out of the box and you won't need to implement any of it yourself, it's still beneficial to have an overview of the flow in mind.
Figure 11.3. The authentication flow supported by the OIDC protocol.
When adopting the authentication flow illustrated in Figure 11.3, Edge service is not affected by the specific authentication strategy. We could configure Keycloak to use an Active Directory or perform a social login via GitHub, and Edge service would not require any changes. It only needs to support OIDC to verify that the authentication happened correctly and get information about the user via an ID token. What's an ID token? It's a JSON Web Token, JWT, containing information about the user authentication event. We'll take a closer look at JWTs in the next section. Note: whenever I mention OIDC, I am referring to the OpenID Connect Core 1.0 specification. See this link. Whenever I mention OAuth2, unless specified otherwise, I am referring to the OAuth 2.1 specification currently under standardization. See this link. And meant to replace the OAuth 2.0 standard described in RFC 6749. See this link. Section 11.3.2. Exchanging user information with JWT. In distributed systems, including microservices and cloud-native applications, the most used strategy for exchanging information about an authenticated user and their authorization is through tokens. JSON Web Token, JWT, is an industry standard for representing claims to be transferred between two parties. It's a widely used format for propagating information about an authenticated user and their permissions securely among different parties in a distributed system. A JWT is not used by itself, but it's included in a larger structure, the JSON Web Signature, JWS, which ensures the integrity of the claims by digitally signing the JWT object. A digitally signed JWT, JWS, is a string composed of 3 parts encoded in base 64 and separated by a dot, character.
See this code?
Note: for debugging purposes, you can use the tool available on jwt.io to encode and decode tokens. As you saw, a digitally signed JWT has 3 parts. Header, a JSON object, called Jose header, containing information about the cryptographic operations performed on the payload. The operations follow the standards from the JavaScript Object Signing and Encryption, Jose, framework. A decoded header looks like this. 1. The algorithm used to sign the token digitally. 2. The type of token.
See this code?
Payload, a JSON object, called claim set, containing the claims conveyed by the token. The JWT specification defines some standard claim names, but you can also define your own. A decoded payload looks like the following. 1. The entity that issued the JWT, the issuer. 2. The entity that is the subject of the JWT, the end user. 3. When the JWT expires, a timestamp.
See this code?
Signature. The signature of the JWT, ensuring that the claims have not been tampered with. A prerequisite of using a JWS structure is that we trust the entity issuing the token, the issuer, and we have a way to check its validity. When a JWT requires integrity and confidentiality, it's first signed as a JWS and then encrypted with JSON Web Encryption, JWE. In this book, we'll use only JWS. Note: if you're interested in learning more about JWT and its related aspects, you can refer to the IETF standard specifications. JSON Web Token, JWT, is documented in RFC 7519, see this link. JSON Web Signature, JWS, is described in RFC 7515, see this link. And JSON Web Encryption, JWE, is presented in RFC 7516, see this link. You might also be interested in JSON Web Algorithms, JWA, which defines the available cryptographic operations for JWTs and is detailed in RFC 7518, see this link. In the case of Polar Bookshop, Edge Service can delegate the authentication step to Keycloak. After authenticating the user successfully, Keycloak will send a JWT to Edge Service with information about the newly authenticated user, ID token. Edge Service will validate the JWT through its signature and inspect it to retrieve data, claims, about the user. Finally, it will establish an authenticated session with the user's browser based on a session cookie, whose identifier is mapped to the JWT. To delegate authentication and retrieve tokens securely, Edge Service must be registered as an OAuth 2 client in Keycloak. Let's see how. Section 11.3.3. Registering an application in Keycloak. As you learned in the previous sections, an OAuth 2 client is an application that can request user authentication and ultimately receive tokens from an authorization server. In the Polar Bookshop architecture, this role is played by Edge Service. When using OIDC/OAuth 2, you need to register each OAuth 2 client with the authorization server before using it for authenticating users. Clients can be public or confidential. We register an application as a public client if it can't keep a secret. For example, mobile applications would be registered as public clients. On the other hand, confidential clients are those that can keep a secret, and they are usually back-end applications like Edge Service. The registration process is similar either way. The main difference is that confidential clients are required to authenticate themselves with the authorization server, such as by relying on a shared secret. It's an additional protection layer we can't use for public clients, since they have no way to store the shared secret securely. The client dilemma in OAuth 2. The client role can be assigned either to a front-end or a back-end application. The main difference is the level of security of the solution. The client is the entity that will receive tokens from the authorization server. The client will have to store them somewhere to be used in subsequent requests from the same user. Tokens are sensitive data that should be secured, and there's no better place than a back-end application to do that, but it's not always possible. Here is my rule of thumb. If the front end is a mobile or desktop application like iOS or Android, that will be the OAuth 2 client, and it will be categorized as a public client. You can use libraries like AppAuth, appauth.io, to add support for OIDC/OAuth 2 and store the tokens as securely as possible on the device. If the front end is a web application, like in Polar Bookshop, then a back-end service should be the client. In this case, it would be categorized as a confidential client. The reason for this distinction is that no matter how much you try to hide the OIDC/OAuth 2 tokens in the browser, cookies, local storage, session storage, they will always be at risk of being exposed and misused. From a security perspective, it is virtually impossible to secure tokens in a front-end web application. That's what application security expert Philippe de Rijk writes. A. Recommending engineers rely on the back-end for front-end pattern and have a back-end application deal with tokens instead. I recommend basing the interaction between browser and backend on a session cookie, like you do for monoliths, and have the backend application be responsible for controlling the authentication flow and using the tokens issued by the authorization server, even in the case of SPAs. That is the current best practice recommended by security experts. P. DeReich, A Critical Analysis of Refresh Token Rotation in Single-Page Applications, Ping Identity Blog, March 18, 2021. See this link. Since Edge Service will be the OAuth 2 client in the Polar Bookshop system, let's register it with Keycloak. We can rely on the Keycloak admin CLI one more time. Make sure the Keycloak container you started earlier is still running. Then open a terminal window and enter a bash console inside the Keycloak container.
See this code?
Next, navigate to the folder where the Keycloak admin CLI scripts are located.
See this code?
As you learned earlier, the admin CLI is protected by the username and password we defined in Docker Compose for the Keycloak container, so we need to start an authenticated session before running any other commands.
See this code?
Finally, register Edge Service as an OAuth 2 client in the Polar Bookshop realm.
See this code?
The valid redirect URLs are the endpoints exposed by the OAuth 2 client application, Edge Service, where Keycloak will redirect authentication requests. Since Keycloak can include sensitive information in a redirect request, we want to limit which applications and endpoints are authorized to receive such information. As you'll learn later, the redirect URL for authentication requests will be localhost 9000/login/OAuth2/code/*, following the default format provided by Spring Security. To support redirects after logout operations, we also need to add localhost 9000 as a valid redirect URL. That's it for this section. In the source code repository accompanying the book, I included a JSON file you can use to load the entire configuration when starting up the Keycloak container in the future. Chapter 11/11end/polar-deployment/docker/keycloak/realm-config.json. Now that you've familiarized yourself with Keycloak, you can update the container definition to ensure you always have the needed configuration at startup. Copy the JSON file over the same path in your own project, and update the Polar Keycloak service in your Docker Compose.yml file as follows.
Listing 11.4, Importing Realm Configuration in Keycloak Container.
Why Keycloak? I decided to use Keycloak since it's a mature, open-source solution for running an authorization server yourself. After increasing demands from the community, Spring started a new Spring Authorization Server project. See this link. Since version 2.0, it's been a production-ready solution for setting up an OAuth 2 authorization server. At the time of writing, the project provides an implementation for the most common OAuth 2 features, and it's currently working on extending support for OIDC-specific features. You can follow the progress and contribute to the project on GitHub. Another option is to use a SaaS solution like Okta, www.okta.com, or auth0, They are both excellent solutions for getting OIDC/OAuth 2 as a managed service, and I encourage you to try them out. For this book, I wanted to use a solution that you could run and reliably reproduce in your local environment without depending on other services that might change over time, making my instructions here invalid. Before moving on, let's stop any running containers. Open a terminal window, navigate to the folder where you keep your Docker Compose file, polar-deployment/docker/dockercompose.yml, and run the following command.
See this code?
We now have all the pieces for refactoring Edge Service so it can use an authentication strategy relying on OIDC/OAuth 2, JWT, and Keycloak. The best part is that it's based on standards and supported by all major languages and frameworks, front-end, back-end, mobile, IoT, including Spring Security.